We're tackling the problem of overfitting in a machine learning model called HistGradientBoostingRegressor, which I use to predict house prices. Overfitting happens when the model learns the training data too well, including the random noise, and performs poorly on new, unseen data. I need to find ways to prevent that. I'm looking at several settings, called hyperparameters, within the HistGradientBoostingRegressor to see which ones are most effective at stopping overfitting. I need to understand how each hyperparameter affects the model's complexity. This controls how much each tree in the model affects the final prediction. A smaller learning rate means each tree contributes less, preventing the model from getting too focused on the training data. This sets a limit to the number of trees the model builds. Too many trees can lead to overfitting. However, this setting doesn't directly control the complexity of each individual tree. This limits the number of leaf nodes, the final decision points, in each tree. Fewer leaf nodes means simpler, less complex trees, directly addressing overfitting. This sets the minimum number of data points required to create a leaf node. A higher value forces simpler trees, making the model less prone to overfitting. This also directly addresses the issue of overly complex trees. I see this as the most direct way to tackle overfitting. By limiting the number of leaf nodes, you're fundamentally simplifying the structure of each decision tree. Think of it like this. A tree with fewer branches, leaf nodes, is less likely to get lost in the details and make overly specific predictions. It's like building a simpler model that avoids getting bogged down in the noise of the data. This hyperparameter directly influences how complex each tree can become. Similar to limiting leaf nodes, setting a minimum number of samples required at each leaf node prevents the trees from becoming too granular. Imagine you only allow a leaf node to be created if at least 10 data points support it. This prevents the model from making decisions based on just a couple of noisy data points. It forces the model to focus on more significant trends in the data, reducing overfitting. This is another excellent hyperparameter to fight complexity in the trees. This hyperparameter doesn't directly control the structure of the trees. Instead, it affects the learning process. A smaller learning rate means that each tree contributes less to the final model. Think of it like taking smaller steps in learning. It's like preventing the model from getting too confident too quickly. By slowing down the learning, you give the model a chance to avoid overly specific decisions and focus on more generalizable patterns, reducing overfitting. It's a gentler way to avoid overfitting. We're tackling a common machine learning problem, overfitting. Think of it like this. Your model is memorizing the training data instead of learning the underlying patterns. This means it performs great on the data it's already seen, but poorly on new, unseen data. We need to fix that. I'll help you choose the best hyperparameters for the HistGradientBoostingRegressor to avoid overfitting. We'll look at how each one affects the model's complexity. This controls how much each tree contributes to the final prediction. A lower learning rate makes the model learn more gradually, reducing the chances of it overfitting to noise in the data. Think of it as taking smaller steps, less likely to stumble. This parameter limits the complexity of each individual tree by limiting the number of leaf nodes. Fewer leaf nodes make simpler trees, which directly reduces complexity, preventing overfitting. Simpler trees are less likely to capture noise. This specifies the minimum number of samples at each leaf node. A higher value means each tree needs more data points at each leaf, forcing it to create simpler trees, making it less likely to overfit. It's like saying, don't make decisions based on tiny groups. Make sure you have enough data to be confident. This sets the maximum number of trees. While too many trees can lead to overfitting, it's not a direct control of the complexity of individual trees. Reducing it might help, but it's not the most direct solution. It's more of an indirect approach. I'm assessing scikit-learn's HistGradientBoostingRegressor, a powerful tool for regression tasks. We're focusing on its hyperparameters, settings that control how the model learns. Understanding these settings helps us fine-tune the model for optimal performance. This hyperparameter dictates the minimum number of data points required at each leaf node of a decision tree. A higher value means simpler trees, which is great for preventing overfitting. Think of it like this. Fewer points at a leaf node mean the model is making more general predictions, which would help reduce the risk of the model memorizing your data. This setting directly controls the maximum number of leaf nodes allowed in each tree. By limiting the number of leaf nodes, I constrain the model's ability to create overly complex trees that might overfit. Each leaf node makes a prediction, so limiting this limits the model's ability to capture very specific data point details. This is a crucial parameter. It controls how quickly the model learns at each iteration, influencing how much each individual tree contributes to the final prediction. A smaller value slows down the learning process. This helps in preventing overfitting, ensuring the model generalizes well to unseen data. Imagine it as a thermostat, with the model learning slowly and steadily, rather than rapidly jumping to conclusions, leading to better generalization. This specifies the maximum number of iterations, or trees that are built. While a large number of iterations can lead to overfitting, it's not directly controlling the complexity of individual trees. Reducing it indirectly addresses overfitting but doesn't address the potential problem of complex trees within these iterations. So, although important, this doesn't target the root cause of complexity like the other hyperparameters. I'm tackling a problem about hyperparameter tuning in scikit-learn's HistGradientBoostingRegressor. I need to find which hyperparameters are best for stopping overfitting. Overfitting happens when a model learns the training data too well, including any random noise, and doesn't perform well on new data. I want hyperparameters that control the model's complexity and prevent this. I will be choosing hyperparameters that can help me address the problem of overfitting. I'm using the HistGradientBoostingRegressor to predict house prices. I've got a decent model, but I'm worried about overfitting. I need to find the best hyperparameters to avoid this. This is the core question. I'm looking for the most effective hyperparameters to tackle overfitting in my house price prediction model. I'll look at each one individually. The LEARNINGRATE controls how much each tree affects the final prediction. A smaller rate makes the model learn more gradually, reducing overfitting. It's like taking smaller steps, making it less likely to stumble. This sets the maximum number of trees. Too many trees can lead to overfitting, so limiting this can help. But this only indirectly affects overfitting as the number of trees itself doesn't determine the complexity of an individual tree. It's like saying, stop building after so many trees. This limits the number of leaf nodes in each tree. Fewer leaves means simpler trees, directly reducing overfitting. Think of it as pruning the branches of a tree to make it less bushy. This sets the minimum number of data points needed at a leaf node. A higher number forces simpler trees, preventing overfitting to small groups of data points. It prevents tiny details from influencing the whole prediction. I need to select every hyperparameter that directly helps to prevent overfitting. I have to carefully consider each choice, applying the knowledge I gained about the individual hyperparameters. This refers to adjusting the settings, hyperparameters, of the HistGradientBoostingRegressor model to optimize its performance. I'll be focusing on how to use these settings to prevent overfitting. Think of it like tuning a car engine. You need to find the right settings for maximum efficiency and smooth performance. This question is asking me to identify the settings in the HistGradientBoostingRegressor model that best prevent overfitting. Overfitting means the model learns the training data too well, including noise, which leads to poor performance on new data. I need to find the settings that will prevent my model from getting too complex and fitting the noise instead of the real patterns. This setting determines the minimum number of data points allowed at the end of each branch, leaf, of a decision tree within the model. A higher value means simpler trees, which directly reduces overfitting, ensuring the model does not become overly tailored to small, noisy subsets of data. Think of it like this. A large value here would encourage the model to make broader, less specific decisions that generalize better to new situations. This refers to the overarching goal of preventing overfitting. Controlling model complexity is achieved by tuning the hyperparameters such as _min_samples_leaf _max_leaf_nodes and _learning_rate . These parameters influence how complex the individual trees in the model are allowed to become and, therefore, how closely the model fits to the training data. This controls the total number of trees the model constructs. While a high number of trees can lead to overfitting, it doesn't directly control the complexity of each individual tree. It's like having a large number of building blocks, but it doesn't dictate how well each block is built. This sets the maximum number of leaf nodes allowed in each decision tree. A lower value will create simpler trees, reducing the risk of overfitting. It's a direct way to limit the model's complexity. Think of it like limiting the branches on a tree to prevent it from becoming overly bushy. This parameter controls how much each tree contributes to the final prediction. A smaller learning rate makes the model learn gradually, reducing the chance of it overfitting to noisy aspects of the data. It's like taking small steps instead of large leaps.